Hello, and welcome to Let's Meet the Virologist, a podcast about the people behind today's virology headlines, people working to understand viruses and how they affect you. We are talking with students, postdocs, and other virologists so that you can learn who they are and what they do. I am Larissa Thackeray, and I am hosting this podcast from America's Heartland in St. Louis, Missouri. On June 21st, 2022, we talked with John Dzimianski, postdoctoral associate at the University of California, Santa Cruz. He got his BSA and PhD at the University of Georgia. Currently, he is using structural biology approaches to understand epitopes on the hemagglutinin glycoprotein of diverse influenza viruses in order to generate a more effective vaccine. Thanks for talking with us today. Why don't you tell us a little bit about yourself?
Sure. So my name is John Dzimianski. I am a postdoc at the University of California, Santa Cruz in the Dubois lab. And our lab is a structural biology focused lab on viruses and virus-host interactions. So really with particular focuses on related to vaccine design or how viruses are modulating the immune responses in the host.
Okay, cool. And can you tell us sort of like way back when, how did you first become interested in science and then virology? What sort of started that journey for you?
I think I have to point back to just the family environment I grew up in. So I grew up in Northeast Georgia, family of 8 kids on a family farm with veterinarians as parents, both practicing. So Dad did big, large animals. My mom did small animals, and so we had animals all over the place. There was constant interactions that we had just in that environment to be close to nature and to be interacting with the world around us. And so a lot of that just facilitated a growing love for those things and an interest in how things work. I mean, we had a lot of other interests too. It wasn't just about nature and science, but that was something that at least laid some groundwork to get there. It took a while for me to get around specifically to virology. I'd say that it really starts back with a core interest in science. So general interest in science, yes, but I really got latched onto science when I was doing high school chemistry, and the textbook that I was going through for that was extremely well written. I felt like I was understanding the world at a core fundamental level. You get later on to college and realize that they're telling you a lot of little white lies and oversimplifying things to just help you understand the core concepts. But that feeling that I was understanding how the world was operating at the most fundamental level was really something that spurred my interest in just learning more. I initially started out as a pre-medical student in college. A lot of that was just the nurturing that I'd had in my family. I guess I have a predisposition to want to help people, and plus just the way that my parents raised me, they encouraged that and encouraged me to think along the terms of medicine and how to apply that. So I started out as a pre-med student and was initially just the classical pre-med student of asking, okay, what in this class is going to help me translate this to some sort of clinical context? But I found over time, and especially as I was kept integrating back to things that were molecular in some nature, like biology didn't have a huge interest for me until I was in intro biology and we were going through DNA replication and transcription and seeing things happen at a molecular level. And that was giving me the same sensation as when I'd been going through chemistry and was feeling like I was understanding basic mechanisms of how the world operated. So the further along I got into college, the more my interest in just science beyond the medicinal applications became something that was just shaping and changing my thinking. So we get all the way to senior year of high school, and that's when the Ebola epidemic broke out in West Africa. And for some reason, viruses just caught my attention at that point. Like Ebola, for some reason, just kind of stuck out. And I was looking it into more and reading about it more. And that didn't turn me into a virologist, but it at least got me to thinking about infectious disease. Like I'd been, just doing the, shadow doctors, trying to figure out what field of medicine I might want to go into. And then this pops up and it's like, okay, well, start thinking more about infectious disease. So that's what started me in being interested in viruses, was that particular subcontext of thinking like a pre-medical student who was getting a growing interest in science, and then just thinking, okay, infectious disease just seems really, really interesting.
Right. And then can you kind of describe sort of to us how you got to your PhD program and to your postdoc? So it's often interesting for other people to sort of hear, how did you choose that institution or those labs? Like, what was it about them that kind of attracted you?
Mm-hmm. So I was one of those undergraduate students that I was having the growing interest in science, and research was intriguing me. I never did undergraduate research, but I kept finding more of an interest in that. And occasionally I'd hear the stories, a professor saying, oh, I was a pre-med student, and then I started doing research, and then I, went and did that instead. And I was pretty steadfast. Okay, I'm interested in research, but that's not going to be me. I'm going to medical school. But I did decide to take a gap year. And in that gap year, I got the opportunity for about 5 months to work as a research technician in a lab while I was going through the application process for medical school. And it wasn't a terrible experience, but it was also a slow learning experience where I was just getting used to the whole dynamic of what a lab research environment is. So I'd say I wasn't necessarily sold on research by the end of that, though it really formed a good foundation for me to figure out, okay, well, what type of research would I still want to explore? And so I'm grateful for the professor who had the patience to give me a few months to start working through some of that. But in that process, I applied to a small set of medical schools and got one interview. And then interview happened in October. We reached January, and I haven't heard back. So then the wheels are going, okay, well, if I haven't heard back, no news probably isn't good news. So what am I going to do if I don't get in this time? And so I started looking. I still had that bug of wanting to really feel out what research was. And I started looking at possible grad school programs, initially thinking, okay, go for a master's, try to do a master's that is focused on research, get the master's, get into a good medical school, graduate, move on. So a lot of graduate school deadlines are way back in December these days, right? So I was already behind the times for a lot of those programs, but started looking around and found a few that I could apply to, including one that was at the same university where I got my undergraduate degree at the University of Georgia. And I started looking at professors, started sending out emails, and had a conversation with one of them. It was just like, okay, here's what my goals are, and he was just saying, okay, well, here's how I can help you get there. And so that went a good ways towards getting me there. One of the reasons I looked at his lab was because he's working on things that were infectious disease related, and specifically he was focusing on viruses. And so it turned out that I ended up going there, and I started doing the master's research and helping a PhD student with her project and learning from her. And I was going through and I was realizing, okay, I'm really enjoying this, and I at least seem to be okay at doing this, and I could maybe see myself doing this long term. So, got through the fall semester, got a good ways into the spring semester, and then started talking to people, and then decided, with the support of the graduate coordinator and my advisor, just scrap the master's idea and change over to the PhD program. So in that process, there's PhD, you're getting into the nitty gritty of a particular thing. And I was just getting fascinated by the molecular interfaces that are involved in virus-host interactions, and thinking down on that core level of, okay, well, why does this virus infect these things and cause disease and not these others? So that's where I think I eventually got sold on virology. Was I had the initial interest, but then it was just working on this stuff and then realizing there are these fundamental questions that are hard to understand. And it just, why does it happen this way? What are the details of how it happens? So I go through the PhD, and I am finding myself at the end asking questions that I didn't have the skills to be able to answer. You're trying to expand beyond the very focused little problem that I was focused on, and seeing where the implications for how that might relate in a larger context, and in systems or on virus protein molecules that are more difficult to work with the techniques that I was using. So that got me to looking at postdocs based on what can I use to apply and build onto my skill set. So I looked at different places, interviewed at different places, and was going at different points in career. I've had these moments where it's like, okay, so what do I want to do now? It's like I had this period of time where it was all clear cut. I do this on a day in, day out basis, and now I have to make that decision again. So it was like over the course of a few months, had some interviews, and then eventually ended up taking this one in Santa Cruz as a balance between being able to immediately contribute with skills I already had, plus to be able to expand into new ones that could help me be able to deal with more complex problems than I'd been able to work on in the PhD.
Right. Cool. And can you tell us then a little bit about that work? I guess sort of the big picture, and then maybe a little bit about the techniques that you use.
Yeah, so I'm a structural biologist, which means that I like to think about things in terms of the three-dimensional structure of the protein molecules. And so what I work on are hemagglutinin protein molecules from the influenza virus. And we're part of a big collaborative multi-institution group that is trying to develop more effective flu vaccine. So we know with the COVID vaccines, there's been the discussion of, okay, we got the vaccines that were like 95% effective, and then variants come out and that effectiveness diminishes. Well, for influenza, we dream of something that was better than 70% on a predictable basis. If you look at the CDC estimates for the effectiveness of flu vaccines for the past 20 or so years, the highest number they give is 60%, and it's usually a bit lower. So we have this big problem that we have all these influenza viruses floating around, but we don't have vaccines that are able to cover all of them. So the point of this collaboration is trying to develop some that will, even if they don't cover everything, they'll at least be able to more effectively cover the ones that are most likely to be of a concern in the next couple of years. So we're taking candidates that are being designed for study in this group, and we're trying to look at it from a structural perspective. So we're taking these virus proteins, we're trying to get structures of them, and look at the structural features to figure out what is it about these proteins that lend them to being broadly protective against multiple viruses versus just a narrow set. In some cases, we're trying to ask, is there something that you miss when you're only looking at the amino acid sequence? Because once you have structure, you get to see things in their spatial context and not just in a 1 or 2D type informational context. So we're asking what are the features that allow this particular protein that we've designed to be more effective, and what implications might that have for how we would design future ones? As a complement to that, when antibodies are discovered in our group that by themselves can broadly neutralize a range of viruses, the natural question is, why can they do that? And what are the limits of what they're able to protect against? So we're also interested in where antibodies bind and what the specific features of that binding are that allow it to be broadly protective.
Cool. And can you tell us a little bit about sort of the different structural techniques that you use to look at the, I guess, the viral protein?
Yeah, so my training in graduate school was X-ray crystallography. So we get a protein. If we can get that protein pure and in sufficient quantities, then we test it against a lot of different conditions to see if we can encourage that protein to regularly order itself into a crystal lattice. And often when you get that crystal lattice, it then has particular features that allow you to collect an X-ray diffraction pattern and eventually, after some computational steps, to recapitulate what the three-dimensional structure was that resulted in that data. And once you get that, you're able to model in particular atoms within that structure and be able to see, okay, so these amino acids that have these functional properties are in close proximity to these other ones, or it's exposed in this way on the surface and might block a particular type of antibody interaction. Another technique that I've been learning since I came to UCSC has been cryo-electron microscopy, which has been one of the big stories the past 5 to 10 years in the world of structural biology. So now you don't need a crystal. You still need a sample that behaves well enough for you so that you can reconstruct what that protein looks like. But it's just an extremely powerful tool that is a good complement to the more long-lived technique of X-ray crystallography. In addition, we have some various biochemical assays. So for testing binding, we're using a technique primarily called biolayer interferometry, where we can determine how quickly, say, an antibody binds to a protein and how tightly it holds on.
Cool. And then I guess, can you talk a little bit more about how you use that structural information to try and build a better vaccine? So what is it about the structural information that you can use to potentially build that vaccine?
Yeah, so one approach that I've taken, and as I've gotten these structures and analyzed them, is to ask what are the structural correlations. Sequence correlation is pretty easy to see because all you need is to know the amino acids and to line them up. But then if you ask the more fundamental question of, well, what really is similar? Are they positioned the same way in space, or has the position of this apparently analogous amino acid gone to a different location? For amino acids that are different, well, how different is really different? Because some amino acids are much different than others, and when you put them into that spatial context, it might matter a little bit, it might matter a lot. So that's one aspect. Another aspect is these proteins are glycoproteins, so they have all these sugars that are coding different parts of the molecule. So a question that we can ask is, well, where are those? And is the position that it's in, could that potentially matter for what surface of the protein is exposed to antibodies and would allow antibodies to bind? And then from the antibody side, it starts out with the core question of what amino acids are forming contacts between the antibody and the antigenic protein. Other labs, will take that type of information, and you can ask questions about, other labs even before our work have tried to do mimicry. So if you know how an antibody works, well, maybe you don't need a full antibody. You just need something that resembles the part of the antibody that is going to bind the same location. So there's different applications that can spring out from that. But the core that we're doing is understanding just at a very fundamental level what's similar, what's different, and what functionally seems to be important when you get into a complex of these two proteins binding together.
Right. And is the idea, though, that information is going to be used to sort of predict how well each individual strain that's circulating will respond to sort of like a pan flu vaccine? Or is it more that you're trying to use that information to actually design a pan flu vaccine?
I'd say right now we're closer to providing explanations for, given this, can we expect it to work against
I see.
these viruses here? The ultimate goal, of course, would be to say, okay, well, we have enough structural information where we could define what structural features we want to say, here are the viruses we want to protect against. Let's make this type of vaccine. That's one of those bridges where it sounds easy, and often it's not quite as easy as it sounds. It's a big success story when something actually works in that with that nice clean application. So I'd say, yeah, the ideal scenario is we're able to say, okay, we want these particular structural features on the vaccine that we're designing, for the next round. Currently, I think we're better set up just to say, with the ones that we already have and that we are looking at the data that other groups are putting in, we can provide a rationale for why we see the data that we see.
Right. And what do you think about, I guess flu is sort of going crazy because the whole ecology of flu is out of whack, as it were. So does this make your data actually more valuable in a way, because it may actually allow us to have a better understanding of when things are circulating, whether we're going to have any protection or not, because there's just a lot of randomness or weirdness that's happening with flu.
Right. Yeah. So the encouraging aspect of the groups that have been designing these proteins, so primarily Ted Ross, his lab for the past almost 10 years, I think, has been applying this technique to try to generate these proteins that are more broadly representative of influenza viruses. And one encouraging aspect is that they designed them and then they seem to be resilient against some of the newer ones that come up. There's a limit. Eventually, a new one pops up that it doesn't protect against any longer. But compared to just trying to make a guess at which strain is going to be coming out, the fact that they seem to at least be partially resilient to the changes that happen in the flu viruses is encouraging. So we can hopefully at least get a good idea of what seems to be circulating, cover a broader range of those than just selecting individual viruses as representative. And then that may buy us a little bit of time as new ones emerge to be able to say, okay, for the next round of design, we can tailor it a bit more to these ones that are emerging.
Right. Cool. And then I guess thinking a little bit about the future, what do you think you will want to do after your postdoc? Do you have any sort of inkling? Are you going to try and stay in academia, go into industry? Any thoughts?
Yeah, my goal right now is to stay in academia.
Okay.
And just a huge benefit of working with my particular PI is that she's really supportive and open to creative ideas. So she's been a good source of feedback on, like, I have this idea that I might want to try to frame up to be a future, to build a research program around. And she's been supportive of trying to develop those ideas. So been able to make a little bit of headway and really gearing up to try to start testing the job market soon. We'll see how that develops.
Great. And it looks like you're giving, I think, a talk at ASV. Are you going to be talking about some of the work that you described today?
Yes. Yeah. So it'll be focusing on a particular influenza hemagglutinin protein that was designed several years ago, actually. And with the structures that we got, we were able to apply some of those analyses that I talked about. So identifying correlations, looking for features that you might not think about just when you look at the sequence alone, as well as an antibody that came as a direct result of this hemagglutinin protein that shows some very interesting characteristics.
Great. Well, thanks so much for talking with us this afternoon, and we look forward to hearing about your results on your talk in ASV.
All right. Yes. Thank you very much. I enjoyed the opportunity.
This has been Let's Meet the Virologist, a podcast about people who study viruses. This is your host, Larissa Thackeray, and thanks for listening. You can find us on Google, Apple, Amazon Music, and other podcast providers, or at lmtv.podbean.com.